Welcome to Chapter 12 on trees. In this chapter, we begin with the question of which Boolean functions are suited for implementation by a tree-like combinational circuit. Namely, this is a combinational circuit which has a topology of a rooted tree. In addition, we'd like to understand when tree-like such implementations are optimal, and by optimal, I mean that the cost is small and that the delay is small. Okay, let's recall. What is a binary Boolean function? A binary Boolean function is simply a function whose domain is 2 bits and the range is a single bit. And often when we have such a binary Boolean function, or a binary function in general, we denote it by a dyadic operator, say a star. Instead of writing f of ab, we simply write a star b. And examples of such operators could be or, and, XOR, and so on. So in the next few slides, when I write a star, it could be any binary Boolean function. Okay, now recall that a binary Boolean function is associative if we have the following equality for every 3 bits. And since we have this equality, we may remove the parentheses. Okay, now consider the function fn, which is defined over n bits by applying the associative function to these n bits. For example, you could define OR n to be the OR of n bits. One way to depict associativity is by the following diagram. Here we have the 3 bits x1, x2, x3 on the left and also on the right. Here we first apply the operator to x1 and x2, and the result we apply the operator together with x3. So this tree corresponds to the expression x1 star x2 star x3. This is the parse tree, so to speak, of this expression. And here I have another way of organizing the operators. I do actually x1 star with x2 star x3. Now, the operator is if the operator is associative, then I know that the outcomes y and z will be equal, and vice versa. If the outcomes y and z are equal for every xy, x1, x2, x3, then of course star is associative. So this is a way of depicting associativity, which I will use later in the talk. Okay, so given a function f, which is a binary Boolean function, we can define fn for domain of n bits as follows. If n equals 1, then f1 of x is simply x. If n equals 2, then f2 is simply f. If n is greater than 2, then fn is defined recursively based on fn minus 1 as follows. If you want to evaluate fn on n bits, you first evaluate fn minus 1 on n minus 1 bits, and the result you apply together with xn the function f, which has a domain of 2 bits. Now, the claim that we want to make is that if f is an associative Boolean function, then the definition of fn equals applying f to a block of n minus k bits with respect to f of n minus k, and the remaining block of k bits with respect to fk. And you take these 2 bits, and to these 2 bits you apply f. And we claim that this equality holds for every n which is greater or equal to 2, and every k which is in the range 1 to n minus 1. Let's try to understand the definition of fn. So the definition of fn says that we apply f to the outcome of fn minus 1 on the first n minus 1 bits together with xn. So if I were to draw this recursion, I have here f, the right operand is xn, the left operand is the outcome of fn minus 1 when applied to the n minus 1 bits x1 up to xn minus 1. Okay? Now we could take this recursion and we could expand it. So if I were to expand it, I would get this tree where xn is the right child of the root, xn minus 1 is the right child of the root, and so on and so forth, until I'm left with 2 bits and I apply f to x1 and x2. Now, we wanted to prove that fn on n bits equals the application of f to n minus k bits x1 up to xn minus k, and the k remaining bits, you apply fk to them. Okay? So, if I were to draw the parse trees of these two expressions, this expression actually says I apply f to fn minus 1 and xn, where fn minus 1 is given the input x1 up to xn minus 1. This is the left-hand side. On the right-hand side, I apply f to two things. The first thing is the outcome of fn minus k. The second thing is the outcome of fk, where fn minus k is fed by n minus k bits, x1 up to xn minus k, and fk is fed by k bits, starting from xn minus k plus 1 until xn. So the claim is that the outcome y equals the outcome z for every input x1 up to xn. Now, if I were to use a value of k which equals 1, then what do I have here on the right-hand side? I have here f of n minus 1, which is identical to what I have here. And here I have f1. And f1 is just the identity function. It just gives you xn. So z and y are clearly equal if k equals 1. Okay? So that would be a very easy case, because the left-hand side and the right-hand side are the same thing. But we want to prove this equality for every n greater than or equal to 2, and for every k, not only for k equals 1, of course. Okay, so how do we prove this claim? We prove it by complete induction on n. And the basis for n equals 2 is true because then k equals 1, and we already saw that when k equals 1, the equality holds. So our hypothesis, the induction hypothesis, is that the left-hand side equals the right-hand side for every n prime which is less than n, and every k which is in the range 1 to n prime minus 1. And now we want to prove the induction step for n. And this will be a very, very unusual proof. I will prove it by pictures. Okay? So let's try to follow what the pictures mean. Okay. I start with f of n applied to x from 1 to n, the n bits of the input. By definition, f of n is applying f to fn minus 1 and xn, where fn minus 1 is fed with x from 1 to n minus 1. This is the definition of fn. Okay, now you notice that I marked this part in red. Okay, good. I expand this part to this part by applying the induction hypothesis. Because fn minus 1, the subscript here, n minus 1, is less than n, I can apply the induction hypothesis to this subtree. And this induction hypothesis tells me that I can partition the n minus 1 bits of input to fn minus 1 as I wish. And in fact, I will partition them to n minus k bits and k minus 1 bits, where fn minus k is fed by the first n minus k bits of x1 up to xn minus 1, and fk minus 1 is fed by the remaining k minus 1 bits of x1 up to xn minus 1. Okay, so the red part here equals the red part here by applying the induction hypothesis to fn minus 1 with k minus 1. Okay, good. Now, let's focus on the top part of the tree, on this part. Now, and we can apply associativity, and we can regard the subtree, the yellow subtree, which has 3 inputs, this one, and this one, and apply associativity to this part of the tree. Okay? So when we apply associativity to this part of the tree, the two f's rotate from this, instead of being the left child, we have a right child. Okay, let's go back to the depiction of what associativity is, and you, just to remind you, to make sure that you see what I'm talking about this associativity by a picture. Okay, so I have three inputs, two applications of an associative function, and I do this so-called rotation. Notice that x1 feeds this one, x1 feeds this one, and so on. Okay, good. Let's return to the proof. So now I apply associativity over here with respect to these three bits. So this bit will feed the root now. This bit will feed will be the left child of the second instance of f, and this bit will be the right input of the second instance of f. So this equality holds by associativity. Okay, this input equals this input equals this input, and this input, of course, equals this input. Very good. Now look at the green part. The green part, we can apply the induction hypothesis to it, because it applies to n, which equals, in fact, k, because we have here k minus 1 bits and 1 bit. So it's n here equals k, which is, of course, less than n, so we can apply the induction hypothesis. And we can say this fellow is simply f of k when the input consists of the k bits starting from n minus k plus 1 until xn. Okay, so this is this fellow. Good. What did we get? This thing corresponds to the left-hand side of what we want to prove. And this thing corresponds to the right-hand side of what we wanted to prove. So we get that the left-hand side equals the right-hand side also for n, and that completes the induction hypothesis, the induction step. Very nice. Now, let's stick to the Boolean function or n, which is the extension of the or of 2 bits to n bits. And let's define a combinational circuit which satisfies 3 properties as an OR tree over n bits. So what is an OR tree over n bits? Of course, it has to be a combinational circuit. The directed graph that corresponds to this combinational circuit is a rooted tree with n sources. These are, or leaves, you can call it leaves or sources, it doesn't matter. And each vertex in this rooted tree that is not a source or a sink is labeled by an OR gate, okay? And the leaves of this circuit are labeled by the inputs x0 up to xn minus 1. So let's see 2 examples. This would be one example of an OR tree over 4 bits. The leaves are labeled by x0 until x3. We have 2 OR gates over here, another OR gate over here, which output y. And this is also an OR tree over 4 bits because it satisfies the 3 conditions of being a rooted tree. Each vertex that is not a source is labeled by an OR, and the labels of the inputs are x0 up to x3. So this is OR tree of 4, not OR tree of 3. Very good. Now, suppose we have a combinational circuit which is an OR tree over n bits. We claim that such a combinational circuit always implements the Boolean function or n. Okay, so it's kind of obvious, but let's try to understand what we need to prove here. We have here 2 different, completely different combinational circuits. For example, in the circuit on the left, x2 and x3 are fed together to the same OR gate. But here, x3 and x2 are not fed to the same OR gates. Okay, so it's not clear that the output here always equals the output here. That's the first issue. And the second issue is it's not clear that these outputs will always be the OR of the 4 bits. Okay, so this is what the claim states. It says that if you have a combinational circuit which is an OR tree over n bits, then it implements the Boolean function or n. Okay, so let's see how we prove it. And the proof method that we will use will repeat throughout today's talk. Okay? So the proof is by complete induction over n. Okay? I'll leave the induction basis and the formulation of the induction hypothesis as an exercise. You could look it up in the book if you wish. And I will now I will prove the induction step. Okay, so in the induction step, I'm given the OR tree over n bits, and I decompose the tree. So I look at the root. This is the root. It is, of course, labeled by an OR. And I look at the left child, the left tree, which is hanging from here, and I look at the right tree, which is hanging from here. Now, the left tree over here has, say, k. Let's denote by k the number of inputs which feed the left tree, and let's denote by n minus k the number of leaves that feed the right tree. And the left subtree and the right subtree are also OR trees because the labels of the inputs are going to be distinct. They might not be contiguous bits x0, x1, x2, and so on and so forth, but we will extend the induction to deal with the fact that the indices here might not be contiguous indices. Okay, so what you would need to say is you'd need to say that the inputs are distinct, okay, instead of labeled x0 up to xn minus 1 for the proof of the induction step. Good. So now you have your subtree, which is an OR tree over k bits, and here you have a subtree, which is an OR tree over n minus k bits. Okay? And the inputs here are called XL, and the inputs here are called XR. And notice that XL union XR is all the inputs, x1 up to xn, or you could call it x0 up to xn minus 1. It's not important. And of course, you don't have a bit which is fed here twice because you want your original circuit had only n leaves, and these n leaves were labeled by distinct bits. So XL and XR are disjoint. Good. Now the induction hypothesis, when applied to the left subtree and the right subtree, tell us that the left subtree implements the OR k over the bits of XL, and the right subtree implements OR of n minus k over the bits of XR. Okay, so what does y equal? Well, y equals, let's see if we could see what y is. Good. Y equals the OR of the outcome of the left subtree and the outcome of the right subtree. But the left subtree, we know that is the OR of the bits in XL, and the right subtree, we know that it is the OR of n minus k bits of XR. By the claim, we can do this partitioning into k and n minus k bits. It does not influence the outcome. It will be the OR of the union of XL and XR. And now all we have to do is rearrange the leaves so that, they go from x0, x1, x2 up to xn minus 1. And that would not matter because OR is commutative. Okay? So OR n, every OR n tree implements the Boolean function OR of n bits. Good. Now, you may ask, what happens if we look at Boolean formulas? Let's go back to Boolean formulas. So we can define what a formula for the OR of n bits is. It is over the variables x0 up to xn minus 1. Every variable xi appears exactly once in the formula, and the only connective which is used in the formula is the OR connective. So if you look at the parse tree of an OR formula, it will in fact be exactly an OR tree. So the claim is a Boolean circuit is an OR n tree if and only if its graph, without of course the inputs and output gates, is a parse tree of an OR n formula. Okay? And I'll leave this claim as the proof of the claim as an exercise. And the hint is, of course, you can prove it by complete induction on n. Okay, so we have here two OR trees over 4 bits. And we notice, so we know by the claim that both of these OR trees compute the OR of 4 bits. Let's count how many OR gates you have in each tree. So in the left tree you have 3 OR gates, and here you also have 3 OR gates. Is this a chance, or is there something here which is some structure? So we want to claim that the number of OR gates, we refer to this as the cost. The cost of every OR tree over n bits is exactly n minus 1 OR gates. So every OR tree over n bits will contain the same number of OR gates, will contain exactly n minus 1 OR gates. This is what the claim says. Okay, we could prove this claim directly. Instead, we will prove a lemma over rooted trees. What does the lemma over rooted trees say? It says, if I have a rooted tree in which the integrity of every vertex is at most 2, and this is what happens, of course, in an OR tree, then the number of vertices in the tree whose integrity is 2 equals the number of sources in the tree minus 1. So let's try to understand why the lemma implies the claim. Okay, so what is the number of sources or inputs in the tree? It will be n. So the right-hand side over here equals n minus 1. And this is what you see over here. This is the n1 minus 1 you see over here. What will the left-hand side of the equality signify? It will equal the number of OR gates in my OR tree, because every OR gate has 2 inputs. So this will tell me, this will be the cost. The cost of the OR tree n is the number of OR gates that appear in it. And the lemma tells me that the number of OR gates equals n minus 1. And this is exactly what the claim states. So the lemma implies the claim. So let's prove the lemma. Okay. So we want to prove that the number of vertices in a rooted tree of integrity at most 2, the number of vertices of integrity 2 equals the number of inputs, or the number of leaves, minus 1. Okay, the proof, as again, complete induction over the number of vertices. The induction basis, when the number of vertices is 1, is simple, because then you have 0 vertices of degree 2 and 1 vertex of degree in degree 0. So you have 1 minus 1 equals 0, left-hand side equals right-hand side. The induction hypothesis says that if for every rooted tree in which you have less than n nodes, less than n inputs. This is wrong, sorry. I want to fix this. With number of leaves less than n, the lemma holds. Okay? Okay, so now we want to prove the induction step. In the induction step, we decompose the tree. So this is the root, this is the left subtree, this is the right subtree. Let's denote by n1 the number of leaves in the left subtree. Let's denote by n2 the number of leaves in the right subtree. Of course, we know that n1 plus n2 equals n. Okay. So the number of vertices of integrity 2 in the whole tree equals the number of vertices of integrity 2 in the left subtree, the number of vertices of integrity 2 in the right subtree, plus 1, because you have the root over here. You have to count that as well. By the induction hypothesis applied to TL and TR, we have that the cardinality of this set is n1 minus 1, the cardinality of this set is n2 minus 1, and we have this 1, and we know that n1 plus n2 equals n, and we get that, what we wanted to prove. Okay, now, there is a case in this proof which I skipped, and that is the case in which the integrity of the root is 1. Because here I did a decomposition, and I assumed that the integrity of the root is 2. But what happens if the integrity of the root is 1? I'll leave this as an exercise. Okay, now I want to define the depth of a vertex in a rooted tree. The depth of a vertex in a rooted tree is simply the length of the path from V to the root. Okay? Unfortunately, in this talk, I will use a non-standard definition of depth. Okay? This is somewhat confusing, so please be aware. I will now define a non-standard definition of depth what you see here in this slide is the standard definition of depth. Okay, so what is the non-standard definition of depth? Okay, so I want to emphasize non-standard. The depth of a rooted tree is the maximum number of vertices with in degree greater than 1 in a path in T. Okay, so what we're doing here is we're only counting vertices along the path of in degree greater than 1. Since we're interested in trees of in degree at most 2, so we're actually counting the number of vertices of in degree 2. So let's look at this example. Here we have a root, its in degree is 2. It has a right child of in degree 1, in degree 1, and so on and so on and so forth until I reach the leaf. What is the depth of the leaf? In this non-standard definition, the depth of the leaf is the number of nodes in the path from the leaf to the root whose in degree is 2. So this fellow has in degree 0, it doesn't count. All the fellows along the path have in degree 1, they don't count. And finally, the root has in degree 2. So the depth of this node is 1, according to this non-standard definition, which doesn't count vertices with in degree 1. Okay? Why are we using a non-standard definition? Well, first of all, we don't want to count inputs and outputs. They're not so interesting. An input has a 0 in degree, an output has an in degree of 1. We don't want to count them. Usually they have a 0 delay and a 0 cost. They don't perform any computation. They're not interesting. The second issue is that by not counting vertices of in degree 1, we are in fact assuming that inverters are free and have 0 delay, 0 cost. Okay? So all the proofs that I will show here will in fact work even if you assume that inverters are for free. Okay, so this is a strengthening of the results. So it's a nice thing to show that for certain functions, it doesn't help to use inverters in order to compute these functions. Okay. A binary tree. A rooted tree is a binary tree if the maximum in degree is 2. A rooted tree is a minimum depth tree if its depth is minimum among all the rooted trees with the same number of leaves. All binary trees with n leaves have the same cost. This we already saw. They have n minus 1 vertices of in degree 2. But which of these trees which have n leaves have also minimum depth? Okay, so we will see two results. So these 2 points need to be proved, of course. The first one is that if n is a power of 2, then there is a unique minimum depth tree. And that tree is the perfect binary tree with log n levels. The second thing that we want to prove is that if n is not a power of 2, then there is more than one minimum depth tree, and we will refer to a minimum depth tree with n leaves, in this case, simply as a balanced tree. So perfect trees are for the case that n equals 2, and balanced, n is a power of 2, and balanced trees is for the more general case where n is not a power of 2. So let's begin with the case that n is a power of 2. Okay. Just to emphasize what are minimum depth trees. Okay, so you see here 2 trees with 6 leaves, 1, 2, 3, 4, 5, 6. Both of them have 6 leaves. And of course, the cost of both of them is 5 OR gates. They have the same number of OR gates. They also have the same depth because the longest path here consists of 3 OR gates. Okay, so they have the same depth. And the question is whether you could find an OR tree over 6 inputs with smaller depth, namely the depth would be 2. Okay, so this is the question. I'll leave this as an exercise. Make sure you know how to answer this question. Okay. Now, we want to claim that if a tree over n leaves is a binary tree, then the depth of Tn has to be at least log n, log base 2 of n. The 2 here is because the tree is binary. The base of the log is 2 because the tree is binary. The in degree is at most 2. Okay. Now, the depth is an integer, so if you want to prove that the depth is greater than or equal to the ceiling of log n, it suffices to prove that it's greater than or equal to log n. Okay? And the proof will proceed by Again, complete induction on n. Okay, so since we saw this structure of a proof a few times already in today's talk, then I will only sketch the proof, and I will skip immediately to the induction step. Okay, so I take the tree, I partition it into two parts, n1 leaves here, n2 leaves here. I know that n1 plus n2 equals equals n. This implies that the maximum between n1 and n2 cannot be smaller than the average, which is n over 2. Okay? Now, I apply the induction hypothesis to the left subtree. I know that its height is at least log of n1. I apply it to the right subtree. I know that its height is at least log of n2. So the depth of the complete tree is at least 1, plus the maximum between the depth of the left subtree and the right subtree. Now we know that the depth of the left subtree is at least log of n1, the depth of the right subtree is at least log of n2. We know that n1, the maximum between n1 and n2 is at least n over 2. So we know that this maximum is greater than or equal to the log base 2 of n over 2. Now 1 plus log of n over 2 is exactly log n, and that completes the proof. Okay, so now we want to look at the case where n equals 2 to the k, and we're looking, in this case, we're searching for a minimum depth tree whose height will be exactly k, because log of n equals k. Okay, so we define the distance of a vertex v to the root. In a rooted tree is the length of the path for v to r. A rooted tree is perfect if the integrity of every non-leaf is 2, and all leaves have the same distance to the root. So here are examples. This is an example with 1 leaf, so the leaf is the root. This is an example with 2 leaves. They have the same distance to the root. This is an example with 4 leaves. They have the same distance to the root. Okay. Now, we want to claim that the number of leaves in a perfect tree is 2 to the k, where k is the distance of the leaves to the root, and equivalently, by substituting n for 2 to the k, we will have that if n is the number of leaves in a perfect tree, then the distance of every leaf to the root is log base 2 of n. Okay, so these two claims are the same. One is obtained by the other by substituting n for 2 to the k. I just want to emphasize that the proof of this claim is, of course, by induction on k, as you can see from these cases. Good. Sorry. Okay, now we want to deal with the case that n is not a power of 2. If n is not a power of 2, we want to construct a minimum depth tree denoted by Tn star, whose depth will be exactly log base 2 of n rounded up. Okay? This is for the case, of course, if n is a power of 2, then log base 2 of n is an integer, and rounding up doesn't do anything. Okay? And in fact, we want to show that when n is not a power of 2, we may have many such trees, more than one. Okay. So let me define what a balanced partition is. Given a number n, we say that a and b are a balanced partition of n if a plus b equals n, and the log of a rounded up and the log of b rounded up are both bounded by log of n rounded up minus 1. Okay, let's see an example. If n equals, say, 13, 13 is 2 to the 4 minus 3. That's 16 minus 3. That's 13. And I want to write the set of all balanced partitions AB of 13. So the first number in this set, the first pair in this set is 8 and 5. So I notice that A equals 8 and B equals 5. 8 plus 5 is, of course, 13. And I notice that log of 13 rounded up is 4. So 4 minus 1 is 3. Log of 8 is 3. Log of 5 is less than 3. So 8 and 5 constitute a balanced partition of 13. And you can check that 7 and 6 are also a good pair, 6 and 7 are also a good pair, and 5 and 8 are also a good pair. And in general, I claim that if n equals 2 to the k minus r, where r is between 0 and 2 to the k minus 1, so in other words, 2 to the k is the smallest power of 2, which is not less than n, then if n equals this 2 to the k minus r, then the set of all balanced partitions is the set of all pairs AB, such that A is between 2 to the k minus 1 and 2 to the k minus 1 minus r, and B is n minus A. So of course A plus B will be equal to n, but I need to show that the log of A and the log of B are bounded by the log of n minus 1. This is a very technical proof. You can find it in the book. I'll skip this proof. Okay. So now what I want to do is I want to construct T n star given a number n, which is not necessarily a power of 2. So the way I do it, if n equals 1, it's trivial. T n star is simply a tree of one node. If n is greater than or equal to 2, then what I do is I partition n in a balanced way into A and B. I recursively construct TA star and TB star. And what I do is I allocate a new root, and I connect TA star as the left child of the root and TB star as the right child of the root, and I get my tree Tn star. Okay. Now we will say that Tn is a balanced tree if it is a valid output of this algorithm for computing balanced trees. Okay. So you notice that here, when I choose A and B, I may be able to choose more than one pair, because, for example, in the case of n equals 13, we noticed that we had 4 such pairs. And we claim that regardless of how we do this partitioning in each stage of the recursion, the depth of the outcome of the algorithm is always log n rounded up. Okay? What does this, before we prove this claim, what does this claim imply? It implies that if we take an OR tree over n leaves that is balanced, namely it is perhaps one of the outcomes, possible outcomes of this algorithm, then the depth will be log n, and therefore the propagation delay will be log n rounded up times the propagation delay of a single OR tree, a single OR gate. Good. So now we want to prove this claim. Okay, so we want to prove that the depth of Tn star equals log n rounded up. And again, the proof is by complete induction on n. I'll skip the induction basis and the induction hypothesis, leave it as an exercise, and proceed immediately to the induction step. I take n, I partition it in a balanced fashion into A and B, and I take TA star and TB star recursively. The induction hypothesis tells me that the depth of this left subtree is log of A rounded up, the depth of this subtree is log of B rounded up. Therefore, the depth of Tn star is the maximum of these two depths plus 1. Okay, now the balanced partition tells me that the maximum of these two logs is less than or equal to log base 2 of n minus 1. I have minus 1 plus 1, I get the log 2n, and I'm done with inequality in one direction. I wanted to prove equality. I have only inequality in one direction. How do I get the inequality in the other direction? Well, Tn star has n leaves, and we already proved that every rooted tree over n leaves has a depth which is at least log n. So this is inequality in one direction, this is inequality in the other direction, and I get the desired equality, and that completes the proof. I want to summarize this part of the talk. We defined what the OR of n bits is. We defined what combinational circuits that are called OR trees over n bits are. These definitions can be extended to any binary Boolean associative function. We notice that the cost of an OR tree over n bits is always n minus 1 OR gates. We define balanced trees, and we analyze the delay of balanced trees and show that it achieves the minimum, which is log base 2 of n rounded up. Thank you very much.